Hey, hi, and welcome to the day 6 of the DP workshop. This is one of the last learning days of the DP workshop. So, kudos to making to this far. And today we're going to talk about optimizing DP solutions, which is one of my personal favorite topics in DP, in fact. Okay. So, I think you might have heard about DP optimization sometime before as well, because we had talked about these things in some of my previous videos. But what exactly is DP optimization? It is essentially the act of kind of optimizing the current solution to its fullest potential. Okay. So there are many times you kind of recognize the correct states, you correct transitions, correct flow, and correct time complexities at times. But maybe sometimes the time complexity is a little over the let's say the limit, the total limit, and you might need to optimize something like some states, some transitions, or something in the whole process, or maybe the memory is a bit more, and then you need to optimize the memory, or in fact you need to use some really cool technique which is actually going to make your code much faster, right? So all of these things are going to be clubbed down in DP optimization, and let's quickly list down what all different things you can kind of tackle when you're like looking at a DP problem. So DP optimization can be something like, let's say, state space reduction. Okay, I'm going to explain these terms quickly as well. So state space reduction means, let's say you have a DP of, let's say, ABC. Okay, DP of recurrence of ABC, and we are caching all the three values in a different array. But let's say C is equal to A plus B, or C is some function of A and B. Okay, in that case, for every particular A and B value, C is fixed. So we don't really need to cache the value of C in an array. In fact, we can drop the parameter C from the DP state and retrieve it from A and B, and that is what is called a state space reduction. Okay. Next is this idea of state rotation, which means we have generally been returning what has been asked in the problem. Okay, but at times we see that there are certain constraint changes in the problem which makes it difficult to kind of do it that way. So what we do is, whatever we were returning, we take that in the state, and whatever we were having in the state, we put back as a return value of the DP. So this is something called a state rotation. Okay, there are more ideas like, let's say, transition optimization. Okay, we can do some sort of transition optimizations if required, and we might also maybe do something like space optimizations if required, space optimizations. Okay, then we can have all sorts of like different more advanced optimizations as well. I'm not going to get into a lot of the advanced part in this particular video, at least, and in fact it's out of the scope for this workshop as well, but I'm going to just quickly list them down so that you can kind of maybe Google them up or learn them up if you want, right? So certain advanced optimizations are like specific techniques for certain class of problems, which it can actually help you to solve in lesser time complexity. Like there is this Knuth optimization, right? In one of the videos I asked that, can we solve the rod cutting problem in better than order NQ, which was the LRDP solution. And it turns out that there is this Knuth optimization which actually solves it in order n square. So this is a really helpful helpful technique for that one problem. In fact, I have generally seen it being used for that one specific class of cost function. Next is, you have something as divide and conquer optimization. Okay, then you have convexal optimization. Okay, then you have something called as alien trick. Okay, you can have simple like monotonicity based optimization. You can have things like 1D 1D DP optimization. Okay, you can have things like sorting based DP optimization, and I can go on and list more and more, but like for now we're gonna stop at this particular place. And these are certain advanced optimizations that might be helpful in certain problems, but since like we are kind of dealing with till the intermediate to medium hard range, we are not going to get into the advanced parts for this particular video. We're going to talk about these first 4 optimizations in this one, and if you want, you can Google them up and learn the other ones if you want, but I think these are not really required at this stage, because if you're kind of doing this workshop, I assume that you're not really 2400 plus on Codeforces or things like that, and generally the questions less than 2400 would not be asking you any of these advanced optimizations. Maybe convexal just sometimes, and maybe sometimes monotonicity based optimization ideas, but never more than that, right? Sometimes maybe sorting as well, but you don't really need all the other things over here. Okay, these are all like, let's say, 27, 2000, 2800 level techniques for DP optimization. But these four are very, very primary, and you would need them for any, like, let's say 2000 rated, or even they sometimes do come up even in coding tests of companies, right? So we're gonna learn them. So the first optimization that we're gonna look at is state space reduction. So let's take a quick problem as a motivation to understand what we are kind of dealing with. So we're given a set of numbers, n numbers, okay, set of n numbers, and you have to find the number of ways to distribute it to two different sets, A and B, such that the sum of set A, when taken remainder with sum of set B, it should come out to be 0, which means like the sum of the B elements perfectly divides the sum of A elements, right? So we need to find the number of ways to distribute it this way. And this is actually a good exercise to do. I mean, by now you should be able to solve this particular problem on your own. But I'm not going to wait for you. It's because this is a recorded video. But if you want, you can pause the video and try it out. And I assume that you are going to do that. Okay. I hope you have gone through at least some thought now. So we're going to solve it with which form? This is going to be a form one problem. Why? Because you have n numbers, and for each one of them you have two choices: go to A or go to B. So what we're gonna do is we're gonna like decide over here, like for the current element, we have to decide if it goes to A, if it goes to B, and at the end when you go to the final index, we need to check whether the sum A divides is being divisible by sum of B or not. So we can keep track of what is the current sum of A and sum of B as well while we are iterating. So if we take it into A, we add it to the sum of A. If you take it to the B, we add it to sum of B. So a very, very natural state choice for this would be dp of level, comma, sum A, comma, sum B. Okay. Now this is the natural like state choice, and we can design the transitions very, very simply. Like if you take an A, you're gonna go to dp of level plus 1. We're gonna have A plus the x of I, and B is going to remain same. Or you can go to dp of L plus 1, A is going to remain same, and B is going to be added with xi, right? So these are the two different options, and like we're going to get the sum of these two because like total number of ways, right? Number of ways. So in number of ways, we add the number of ways. So this is the whole state idea, but the state space reduction happens over here because at any point in time when you're dealing with this element, right, you have dealt with all these elements. Since when you are at a particular level, the sum of these elements are fixed, right? That is nothing but, let's say, the prefix sum of level minus 1 or something like that. It's a fixed number, right? So if you fix the level, this sum is fixed, right? Now this sum is nothing but equal to, can I say that this is going to be equal to sum of A plus sum of B? Okay. And that is going to be nothing but, let's say, the prefix sum of level minus 1. I mean, I'm not explaining prefix sum right now, but it's a general idea that like whatever sum till this much is, that is going to be equal to sum of whatever elements you have taken in A, whatever elements you have taken in B. We are distributing all the elements in the two sets, so it's going to be like combined over here. Now, if we have this function, we know that sum of B is going to be equal to prefix of level minus 1 minus sum of A. So we can drop this parameter in the DP state, okay, and not even cache it in the array. So that will like lead us to a smaller like state solution. So the total time constant will decrease, right? Because earlier we had to add this into the total number of states possible, the formula that we have, right? But now this will be removed, and we can at any point in time, if you need it to check, like let's say if level is equal to n, we can find out the sum of B as equal to the total minus sum of A, and then use this number to check if, let's say, sum of A mod B is equal to 0, return 1, or else return 0. These all things we can do directly over here, right? So if you just keep track of sum of A, we know the sum of B. So if something can be deduced out of these two variables, then we can omit it off from the state. But please don't do it unless it is not the case, okay? If it is not possible to retrieve it out of the other two variables and it is kind of fixed, don't do this. This is an optimization. I personally feel that some people kind of take optimizations and just apply it to every problem. That is not going to work, okay? Understand when we are doing it, when it is dependent, when it can be written as a function of the other state variables that you have, okay? And it's a unique value. So that is what is the idea of state space reduction. We're not solving this problem because we have solved similar problem before in the workshop, and I feel this is possible to be solved even by you. So I would leave this problem to be like maybe solved, coded by you itself, just to practice if you can write these codes. But again, I think this should be feasible for you at this particular stage if you're seeing the day 6 video now. Another idea that we have in DP optimizations is state rotation, which is in fact the problem. If you have seen this problem, we have discussed this before as well. This is at coder E, right? This is at coder DP contest E. So this is one of those unique ideas which sometimes happens to happen, which is the concept that runs over here is DP of, so we return something in the DP, right? What if the return value, like let's say over here level, okay, in the earlier case, in case of knapsack, what is the sum that you have taken that you had to keep, okay, and what is the value made, okay, value that you have made till now, what is the value that you have made. So what we were doing was we had a unique combination at a particular level. We would have certain sum taken and a certain value made. We were returning this value and we were keeping this in the state, okay. This 3 is a unique combination. It is either going to be possible to hit it or not. So what we were doing was we were returning the optimal value that we can make and we were saving the sum taken. Sometimes what happens is that even if the question is asked as what is maximum possible sum taken, sum of the VIs, the sum of the values, okay, value maximum, even in that case we can keep track of this DP of level and what is the current value taken as of now. And in this case we can return minimum weight to make this value, okay. What is the minimum weight in which you can make this value? If for a certain value taken, if for a certain value taken X, if the minimum weight to make this value is going to be equal to less than equal to W, then it is feasible. If it is greater than W, then it's not feasible, which means if for a certain value that you have to take across all the elements, let's say this level is equal to 0, right? If you have for a particular X, the minimum weight by which you can make this value, minimum weight that the knapsack should have by which you can make this value is less than equal to W, then we can make it, right? And or else we cannot. So that's the idea, that this answer is also like part of the state itself, and this is like a whole trio which is a unique combination, and we return the value which is being asked in general cases, in 90% of the cases that you're going to be seeing. But it is quite possible that for certain problems we might rotate the state and return something else, not the one that is asked in the problem. So keep this in mind. This might be handy in certain problems, though I feel this is quite rare, and at least if you're sitting for coding tests and interviews, I don't think you're going to be seeing this over here, okay. But still, this is something which is possible, so keep this in mind, okay. Okay, so till now we have been doing quite a lot of theoretical stuff and not solving a concrete problem. So let's get into a concrete problem and learn certain optimizations out of that, right? So this is one of my personal favorite problems, in fact, out of the whole workshop, if I had to pick one, right? Let's say there is this person who is standing at a city 1, okay? This is cities, okay? This is city 1, 2, 3 up till n. The person is standing at city 1 and he needs to go to city n, okay? Now, he can go from any city I to I plus 1 using a bus. So there is a bus service between every two cities. So there is a bus which runs between these two, there is a bus which runs between these two, there is a bus which runs between these two, and so on, right? So B of I gives me the bus cost, like the cost of the ticket of the bus, let's say, to move from, let's say, 2. So B of 2 will give me the cost to move from 2 to 3 in this whole setup, okay? Then B of 3 is gonna give me the cost to move from 3 to 4. Similarly, B of n minus 1 is gonna give me cost to move from n minus 1 to n, and I want to go from 1 to n, okay? So one option, if the buses are available at every place, you know that buses are available at every place, which might not be the true in all cases, but still you can go directly like this by taking all the B values and just use them to find out the final best answer in which you can reach. I mean, that is going to be summation of the B array, in fact. How many elements would be there in the B array? 1, 2, 3 up till n minus 1. So there are n minus 1 elements in the B array, which is going to give you the cost to move from I to I plus 1 as the BI. So BI is nothing but the cost to move from I to I plus 1. City number I to I plus 1. Now, obviously the question is not that easy. So we now have an aeroplane service as well available in the cities, which you can opt at any particular point in time. And it has a certain AI array given to you as a parameter. Let's understand. So from a certain place, you can decide, okay, I'm going to take a flight. So to take a flight, you can jump at most k step. So you can, from an I, you can go to I plus j, where j belongs to 1 to k. So you can go 1 step, 2 step, let's say k is equal to 3. So you can at most go 3 steps, okay? And if you fly from, let's say 3 to 5, let's say you go from 3 to 6, you're going to get the cost of the air flight as a of 3 plus a of 6. So it's kind of like the cost of departure plus cost of arrival, right? So generally that's where the most of the cost happens for any airport as well. So we're going to assume that for this particular scenario, if you fly from any city I to I plus j, the cost is going to be equal to ai plus j, which is nothing but the a values of the two cities from and to, okay? So that's the cost to fly from I to j, and you can move only k steps. So the input contains n, m is not really there right now, k is present, a and b is present over here, right? So these inputs are available to you, n and k is given, a and b arrays are given to you. You have to find the minimum cost path that you can use to move from 1 to n, and that's the whole problem. Okay, I kind of speeded through all the problem. I mean, I think it's clear, but if not, just go back, rewatch the video of the question, and then we can kind of move to the solution. That's the best part of recording videos, that I can ask you to go back and see, not in live classes, right? Anyways, so what have we as a problem over here? Okay, a very, very interesting suggestion. Please pause the video and solve this problem on your own. I think you should be able to solve it at least in the naive complexity. Maybe we will use some DP optimization to optimize it further, but try to solve this problem directly on the first glance, okay? So over here we have a problem, right? We're going to use the standard framework that we have learned in the whole workshop. Which form this problem looks like in? Guess which form does this looks like? I mean, not a guess actually. You have path written over here, right? It's a big key that you are jumping something like this. Whenever you see jumps like this, it is actually form 2. Okay. Naturally, form 2 should come into action when you have subsequences or jumps or paths in some place. Most probably a form 2, because paths are like kind of joining of many different interactions or many different moves, and you can kind of trace back the last move. That's how the form 2 works as well, right? So over here we have, for form 2, we can try and model this particular problem, and we know it's an ending state dp. So we're going to write dp of, let's say, some city, some index or some level, just so that you guys, we are consistent with the naming. Anyways, namings and all is all up to us, okay? So it is going to return the whatever is asked, min cost path from 1 to n. It is going to return min cost path from 1 to level, okay? So what is the minimum cost path ending at this particular cell, okay? That's the what we're going to return at this thing. So this is the state step. This is the second step, state. Let's try to write down the transition real quick, okay? Transition. Okay, so how do we find out dp of level? Okay, so if you are at a particular state over here, let's say some level over here, okay, how do you reach this particular level? Maybe you took a bus last time. What was the last thing that you did? Maybe you took a bus and you went to level. So in that case, maybe one option is bus, okay, bus. In that case, you can use something like, you need to come to the, like if you use the bus, you are coming from the last city, right? So you have to come to the last city and then take a bus. So dp of level -1, come to the last city plus the bus cost of last city. That is going to be the total cost to reach this particular thing, because this is going to find you the best way to reach the last cell, and then you're going to take a bus. Or else if you took a flight, you have a lot of options now, right? Now, where could you come from? You could have taken it from 1 to 3. Let's say k is equal to 3. So you can take out of flight from these 3 things, because from this you can reach to 3, like I plus 3. From this you can reach to I plus 2. From this you can reach to I plus 1. So I can come from dp of level -j, okay, where j is gonna range 1 to k, right? From all these things, I can come to this particular state, plus I'm going to fly out from this particular city. So a of that city is going to get added, okay? plus I'm gonna land at this particular city. So A of level is gonna get added. Okay. So that is the total cost to reach this particular place if I come from this particular city with a single flight directly. So that's the last transport that I took. Okay. So these are the two transitions, right? And this seems very simple, right? We have, like, let's say, let's try to do the time complexity stuff as well. What is the number of states? Very simply, the number of states is going to be n. Okay, number of cities. What is the number of transitions? In this path, you have a bus which is only one, plus in this side you have a flight which has k different options, and you need to take the, out of this you're gonna take the minimum, right? So 1 plus over here you have k options. So in total you would have an order n into k solution over here, right? This is the direct solution that you can use for this particular problem. Order n into k solution can be found out very easily, right? So this is fine. Let's just quickly go ahead and code this particular solution as well. I'm gonna this is going to be quickly as a revision video as well for the whole things that we have learned all across the whole workshop as well, so that it just jolts up your memory in case you have forgotten all those things. Okay, so let's go to the code. So let's go ahead and quickly code the recursive version of this particular code. So I have an integer level where I want to end, and I am going to get the inputs as well. So integer n, k is there as an input. I have integer a and the b array. So I'm going to take it somewhere over here and really care right now. Okay. So this is going to be the a array. This is going to be the b array. I don't care what the values are right now. And for now, I'm not just like considering like integer overflows and things like that, because we're not dealing with modulos and stuff in this problem. I hope you guys would be able to handle that when it comes up in the real problem. So I'm going to assume that everything fits in integer. No like variable overflows and stuff like that is going to be problematic for now. So pruning doesn't really require that. Let's write the base case first. So whenever I write things, I try to write the base cases first, and based on transition, I try to write pruning over here. So when you have level is equal to n, so we have reached the level equal to 1, which is like what is the best path or the cost to reach the first city, which is going to be return 0, right? Because you're already at city 1, so you don't really need any cost to reach the city 1. Next is cache check. So it's going to return if dp of level, the cost is going to be always positive. So I'm going to assume that things are always positive. So if it's equal to -1, if it's not equal to -1, then it means it has been saved with some value. So I'm going to keep dp of level as the return value over here. So this is what is going to be returned, or else you compute the answer. So integer answer is going to be equal to, by default you can come with bus maybe. So since it's not 1, we can always use the previous index. So we're gonna go ahead and take cn, not cn, we're gonna take, you come with the bus from the last index. So recurrence of level -1, you come to the last index and then you take a bus. So at the level -1, you're taking a bus. So it costs you level of b of level -1, right? And another option is that you take a flight. So for integer for integer j is equal to 1, j is less than equal to k, j plus plus. Okay. Now I'm gonna go in answer equal to, okay. I'm gonna minimize the cost. So min of answer, comma, let's say you're gonna come to the recurrence, you're gonna come to the level -j, and then you're gonna take a flight from there. So a of level -j is gonna be there for the departure, plus for the arrival there is another cost which is a of, let's say, j, okay, a of level, right? So that is the cost for this one, and across all whatever is the best is what you find in return. So return dp of level equal to answer. This is what is like the full code. In fact, one simple thing, in case you go across at any particular state, let's say j is equal to 1 up to k, and what if level is less than k? In that case, this is going to go to negative values. So one simple way in which you can handle this is if level is less than 1, in that case you can return, it's not possible to go there, right? So return, it's going to be used as a plus, right? Everything is plus, so you're going to return positive infinity. So we're going to return infinite value. So I'm going to, let's say, declare something over here, constraint infinity, integer infinity, let's say I'm going to call it infinite, let's say 1e9. It will depend on the problem. Generally it's going to be kept as a very high number, so you can keep anything. I'm going to keep infinity over here. Okay, it's not possible to go with this many, like to a level less than -1. So in that case, what will happen, see over here, this is how pruning works without writing the check over here. Like you could have written an if else over here. If let's say this is feasible, then go there, but I'm just writing a pruning to show you guys. So if you go to level minus j, it is going to go to this code and it's going to return infinity. So this is going to return infinity. Infinity plus anything is infinity. So we are taking a minimum. So it will always take the other part, right? So it's like this is not a feasible transition. That's how this like returning minimum, returning positive infinity for minimum problem works. Okay, so that's the basic recursion code. But for this particular problem going forward, we're gonna try and make it an iterative code. So let's quickly also go through the iterative ideas and how do you convert things to iterative idea. The next step that we do in generally for such problems is to think about the order of loops. Since level depends upon level minus 1, we're gonna loop forward, okay? Which means we're gonna go from 1 to n, okay? Because for level, you need to have level minus 1 computed or level minus certain j is computed. So we're gonna loop forward. So if I had to calculate this in an iterative way, what I would do is, and I'm not writing the call function to this one. I think that is way more simpler now for you guys. So I'm gonna write the iterative code directly. So let's assume that this DP array is over here, and I'm gonna create the DP array over here. DP110010, let's say, right? And I'm gonna just simply create the DP array. So DP of, let's say, 1 is equal to over here as 0, right? For integer I equal to 2, I is less than equal to n, I plus plus, right? I'm just taking through this. We have an input version as well. Let's call a void input. Let's forget about the input things over here. Let's say the input is gonna be taken over here like n. Since I'm writing the code, let's just write it. It's hardly gonna take me like quick 10-20 seconds. So we're gonna take the for all the indexes, we have an a of I value. Okay, so we will take an a of I value, the aeroplane arrival or departure cost of that airport. And for integer I equal to 1, we will not go till n. This time we will go till n minus 1 because the buses, like from I minus 1 you can go to n minus 1, you can go to n. So there is nothing beyond n. So we can just take the scene p value till that point, and that's the whole input. Once we have the input, we're gonna like start with dp of 1 equal to 0, and we're gonna loop through all the arrays, and for each of them I'm gonna use the same recurrence, right? So dp of I is going to be equal to, by default it is nothing but this part. Okay, so I can actually copy paste this thing and maybe write it that way if it's easier for you to think that way. So by default this is going to be this, and since we are using only dp array, we're going to replace the recurrence with dp array. And for different transitions that you have over here, for j equal to this, in this case you cannot really write a pruning. That's the bad part of writing iterative codes, that you cannot really like return if things are not feasible. So if level minus j, okay, we have a level over here, right? So I'm gonna just keep the level intact. Okay, if level minus j is greater than equal to 1, then only you can go to that particular thing. So answer is nothing but dp of level itself. Okay, if this is the case, then dp of level, one more option for my dp of level is going to be equal to go to dp of level minus j, okay, and do this. So if it's feasible to go this way, then take a minimum width, come to that particular part and take a plane, right? This is something which we have over here. So this is how we can code it in an iterative manner, and you can simply return, let's say, cout dp of, let's say, n to give the answer. That should be enough. That should be all there is to the code. Okay, and this is the recursive version, this is the iterative version. I've shown you both the versions now, right? But now we're gonna see an optimization where maybe the iterative version has a bit of supremacy. So let's see. So what are we kind of dealing with over here? To find out a certain value over here, let's say some certain dp of I, we want to calculate dp of I. We need two things. One is dp of I minus 1. Okay, that is fine, dp of I minus 1. But one more thing that we require is, for all of them, like for all different j's in the range 1 to k, you can come from dp of I minus j plus a of I minus j plus a of I. You can come from any of these, right, out of these k, and we have to loop across all of them, and that is what is increasing our transition. Okay, transitions. So we can try and do a transition optimization over here, which is going to help us find out this minimum across all these options faster than what we are doing right now. Okay, how is that? I mean, how do we find out the minimum across all of these things quickly? So we know the dp of I minus j, so these dp values are readily available for us. We can kind of do a plus a of I minus j, so we can write this, we want to find minimum across all of these things. So this a of I is fixed across all j, so we can take it out from over here. Okay, and this is what we want to minimize. Okay, and it's bunch of values like dp of I minus 1 plus a of I minus 1. Okay, these like and so on, right? These values. Note that we need to find out the minimum of this to be used over here. Okay, now for the similar type of values, we also need the minimum of this to be filled in over here. We need the minimum of this to be filled in over here. So let's say if you create an array, let's say something like c, which is equal to dp of c of, let's say, some I, index I, is equal to dp of index I plus c plus a of the index I. Okay, if this is the new array c, isn't this minimum nothing but min of the c array in the range, let's say, I minus k till I minus 1? We need to find the minimum in this range for the c array. And since we are doing iteratively, we can, as we calculate the dp of I, we can calculate c of I incrementally as well. So at any particular index, we can find out the minimum of the last k. Then for any index, we can find out the minimum of the last k of this new c array. We'll not create the c array, just wait for, I understand this might be becoming a bit difficult right now to kind of grasp. But what we're trying to see is that we need minimum of very, very similar kind of values from the last few things. Okay. So over here, in this optimization, across all these loops, if I can find this minimum in almost order 1, then we can maybe do this whole transition in order 1 and it would optimize a lot, right? So the problem kind of reduces down to finding the minimum of the c array for every k window. Okay, for this index you need this k window, for this index you need this k window, for this index you need this k window, right? So for every element you need a k window minimum of a certain c array, which is getting computed as you go on, right? As you calculate dp of I, you know the value of c of I as well, because a is fixed. So we need k minimums of k windows of a particular array. Does this problem sounds similar to some other problem that you have solved? If not, there are multiple ways to do this, using multiset, using some data structures. But what I'm going to show you is the most optimal one, which is using something called as monotone DQ. Okay, I will not be explaining the whole solution of this particular problem in this video, because that is another like classical problem which has an order n plus k solution. Okay, but there is this monotone DQ which solves this problem very, very neatly. Okay, the way it does it is it like recognizes this need that for, let's say, for this index, the answer was calculated using this particular setup. Now to find out the answer for this, we need to remove this element so that the k window moves one step forward, remove, and find out the new minimum. If we can support these three like operations, remove, insert, and minimum, then we are done with the problem. A multiset can very well do this in n log n kind of complexity, but there is a monotone DQ kind of structure which works specifically for this kind of a problem, where you're inserting numbers from this side and you're removing numbers from this side, and you want to find the minimum of the window. In that case, we have a linear solution for this. So you can Google this up, finding minimum of every k window, every k length subarray. This is a very, very classical problem. You will find the DQ solution directly. I'm going to quickly write the code, maybe just explaining it in a very, very short way. Since we are like going to use the iterative code forward, I'm gonna let's keep the recursive function. Anyways, we're not using them. So over here, we're gonna write the structure. So struct monotone DQ. Okay, so we're gonna write the structure real quick, and that is going to be helpful for us to kind of support this in order n time in total, or order 1 with it is going to give us an armatized order 1 insert, order 1 remove, and order 1 get minimum. So we need to support void insert a number integer x from this side for void remove a number from the other side, and let's say integer get minimum, right? I'm not assuming that we are gonna overflow integer at any point in time. The way this works is I'm gonna just quickly implement this for you guys. You can do it, learn about this particular problem separately and then solve this problem if you want to do it. But for now, just understand that there is this classical structure which solves this in O of 1, all of these things, okay? Insert armatized order 1. Insert of x, what we do is while not dq dot empty, while it's not empty, and the element at the back is bigger, so we are finding out the minimum. So, and dq dot back is strictly bigger than the current element x. In that case, the element at the back can never be the minimum. So we can do dq dot pop back. This is something that happens as long as it's not empty and this is true. And then what we do is we insert at the back, push back x. Okay. When we want to remove an element, just see if dq dot, if not dq dot empty, if it's not empty, obviously we need to check if it's not empty. If dq dot front is equal to what do we have it equal to if dq dot front is equal to x, dq dot pop front. If the element that needs to be removed is in the front, then remove it, or else it has already been removed. I'm not putting up, like, let's say the explanation of this particular problem. Maybe if you go to I will think about this particular thing, but maybe I will put up a quick bonus, let's say, lecture in the content in the course on the website, and from there you can watch this particular video. On that I will maybe include this particular video so that you can kind of learn how this structure works, why this works, and things like that, how you can solve it on your own as well. Pop back. So this is something I've taken long back as a live lecture back in AlgoZenith, but I will add it for this particular workshop too so that you can watch it. Okay, so this is dq dot pop back, and this is going to be the remove part. Get minimum is very, very simple. If not dq dot empty, I'm going to return the front is always going to contain the minimum element, okay? Or else I'm going to just return 0. Okay, no worries on that, okay? So this is how a monotone DQ like implements. You can insert a number from this side, and you can remove a number from this side as you're like kind of going on. And as you keep on inserting more and more numbers, you are gonna get a like O of like each insert, remove, and get min is armatized order 1. Sorry. So this is what we can use over here to optimize this like k loop transition. So when you are like looping at a particular index, we need to ensure that you have inserted the previous indexes as like required value. So we're gonna create a monotone DQ, DQ, right? That's what we will do. And for this DQ, what we'll do is we will keep track of everything that we have done for the previous level. So it is going to maintain, like, it is when you're solving for a level I, it is already containing the window I minus 1 to I minus k. So we're gonna only change for certain things. DQ dot remove. So we are gonna insert the C value, which is nothing but I'm gonna do it this way itself. So we're gonna insert. So when you're processing 2, you need to insert 1 because that is now no longer in the current window. Insert dp of level minus 1 plus a of level minus 1. And you need to remove certain thing which is like long back added. So let's go ahead and quickly compute the indexes. Okay. If you are dealing with this, if you are at so currently the window contained this and you were at some index x. So when you're moving to x plus 1, let's say this is equal to your current level, okay? You had all these elements C values in the window. So I need to insert this one also in the window, and I have to remove this one from the window so that I go to the next window. So for a particular level, I need to insert level minus 1, and till this much it's level minus k. because that needs to be included. So this one is level minus k minus 1. I'm going to remove that index out of the DQ, the value from the DQ. DQ dot remove dp of level minus k minus 1 plus a of level minus k minus 1, provided that this index exists. So if this index is greater than equal to 0, provided this index exists, this is greater than equal to 1. If this index exists, then only we're gonna do this. Okay, so this is gonna maintain the DQ, and instead of finding this minimum directly, we can do dp of level instead of this like whole minimum stuff. So we don't need the loop anymore. If you maintain this DQ, dp of level is going to be equal to minimum of this. So across all different j's, the minimum of this is going to be returned by DQ, the DQ dot get minimum. So whatever the DQ remembers as the get minimum plus a of level, so that minimum will be returned plus a of level will be the like arrival cost. So best reaching plus departure, that you find out the minimum cost out of that, and then you arrive over here. It's independent of that, so you get that added over here, and that's the minimum that you can do. Okay, so this inserts and remove are going to work in armatized order 1. So this whole code now becomes an order n, right? The transition now becomes order 1 on an average case. That's the beauty of this optimization, that when you have a certain problem where there is a minimum or a sum that you need to compute for a certain value, maybe you can process some sort of data structure on top of the previous DP values or something like that. Let's say prefix sums or data structures on top of certain previous DP values that can help you calculate the needed value in a much faster way. And this is an example of that. Okay, so this is how we solve this particular problem in O of n plus k. This is an O of n plus k solution because DQ takes the order n plus k. This code over here is order n plus k, whatever the window size is, which is order n. So this whole works in order n now. So we removed a k from the whole complexity. Now it doesn't really depend upon k, right? And that's really phenomenal because like suddenly some magical structure came into being, and we are now like a k less, right? Okay, so even if like you're little uncertain due to this DQ being seen for the first time, I'm gonna assume that from now this is gonna give you the you can insert, remove, and find out the minimum of a DQ very easily. And if you add these values in the DQ, you're gonna get the correct value accordingly. Okay, now we're gonna make the problem a bit more complicated. We just add one simple line. We're gonna write, what if at most m different flights can be taken? What if m flights can be taken? Okay, what if m flights can be taken? At most n flights. So we have a restriction on the number of flights that we can take now. Okay, how to model this? M flights taken can be taken. Very simple, right? This is also a form 2 problem. But now when you're ending over here, okay, just to make sure that we are not exceeding the number of flights, we have to keep track of that too. That, okay, we are going to end at this index, but what is the number of flights used? What is the number of flights used? That is also something we will put in the state, because remember, the simple rule is whatever new constraint to the solution gets added in the question, correspondingly we might try to add things to the states so as we can check that efficiently. Okay, so the number of flights that is used for now is added over here. Okay, so that's the whole idea for let's say this addition over here. And let's quickly just write the transitions very, very simply. So dp of, I'm going to write index as I from now on, okay, or level as I plus, so this should have been level as I from now on, and number of flights as, let's say, j, okay, just to make it more simpler, or maybe it will become complicated. What do you think? And we can keep j, no problem. Okay, so number of, this is the which level you are at and which flight you are currently taking. Okay, so a number of flights that you have taken till now, ending at this particular place. So maybe you took a bus, so you're gonna go to dp of I minus 1, and you have not taken a flight last time, so you will reach I minus 1 with j flights only, and then you will take a bus plus b array of I minus 1. Okay, and if you take a flight from, let's say, some certain place, dp of, let's say, I minus x, where x is in the range k to 1, right? And you will use a flight, so Till that point, you need to reach in j minus 1 number of flights plus a of I minus x plus a of I. Right? This is the transition in case you add this number of flights into the state. This is a very, very simple addition over here, right? I can throw in more and more constraints and you can keep adding them in the states. That's all there is to it. Okay. So now this will perfectly model, like whenever you're using a flight, you're decreasing the amount that you have. So in that case, whenever you want to find out you want to reach the particular level with a certain number of flights, then you can find out that answer because you're decreasing the flights, and at certain point in time, it will not be feasible to take any more flights. I mean, this will be blocked if j is equal to 0. If you have to reach here without using any flights, then you cannot go this way. That's the main blocker. Okay, so if this is there, let's try to kind of change the code and maybe just inculcate this new state over here in the code. Okay, I'm doing this just so that I can show you one more optimization. Okay, so we had kept this over here, right? Maybe, just maybe, what we can do is we can, like, let's say keep something so one simple idea. Okay, integer, let's say you have the number of flights. Okay, this number of flights, let's say it can be about 100, let's say, so you keep it over here. Okay. So, or let's say up till 1000, it can be up till 1000, so you keep it over here. It is equally possible to kind of shift it to this particular side as well, because it's going to be just like this. If you have this num over here, I'm going to write the iterative code real quick. If you have the num over here and you add this particular thing over here, you can write the num, some base cases would change over here depending upon the num. Okay, obviously this is going to be possible if only if num is greater than 0, and we are gonna be going to and if not, like when you're at 1 and you have to use 0 flights, then only you get a 0, or else there is no way to, I mean, I can allow any way to kind of reach with 0, like any number of flights you can get to 0, but I'm gonna just do it strictly return infinity. Okay, I'm gonna return infinity in case you have a level equal to 1. Like if you want to reach 1 with 2 flights by taking 2 flights already, how can you do that? You're already at 1, you'll not be taking any flight, right? So you cannot do that, so it is going to cost you infinity. And this is going to be the transition added over here. Since we're taking a bus, we don't really reduce the num, but if you take a flight, you're going to reduce the num minus 1, and that's the whole code. In fact, just added a new parameter and changed the transitions a bit over here and there, right? That's the whole code. Okay, so you added this number, and let's say the number was up to 1000 or so. Okay, now a very, very simple and interesting learning. Okay, generally when you have an array, keeping a smaller state in the front is going to be helpful and faster. Okay, remember, whenever you have a smaller value over here, try to keep it in the memory location in the front. Reason being, because it's all about this caching optimization that happens in codes. I'm not going to get into that particular thing, but there is a lot of caching optimization that happens behind the scenes when you're writing these codes. A lot of these values get read together, so you can keep the number over here, like instead of even if the parameter is in second, you can keep the saving value in the first, and it doesn't really matter, right? Because you're accessing just an array index, so how does it matter if it's coming from the first value or the second value, right? That's something which is always there. It doesn't really matter whether it's coming from the first value or the second value. What matters is that is it being saved at a unique place. That's the only thing that matters. Okay, so that is something we can do over here. We can keep the nums over here and we can keep the level over here, right? But again, as we have been doing till now, we have to use iterative code. So how do we convert this double parameter code into iterative code, right? So for a particular level comma num, we see that it depends upon level is lesser and even num is going to decrease, right? So let's try to think it this way. For a particular index, let's say this is the row is going to give you the number of flights, because we are having the number of flights in the front, number of flights, and on this side you have the number of, not really number of, okay, not really number of, it's going to be, what do we have over here? This is going to be the level index that you have to end at. Okay, and to end this at this particular place, you might come from the last index with the same number of flights, or you can come from any of the previous indexes but one flight less and take a flight. Like from this you can take a flight, from this you can take a flight, from this you can take a flight, right? These are all like 1 index, 2 index, 3 index previous values. From these you can take a flight. So these states needs to be calculated when you are calculating this. So a very natural way to progress through this is just loop through the values in this order. Okay, when you reach this, this is calculated, this is calculated. Okay, so we loop through the number of highs and then the number of flies and the flights that you have taken and the number of indexes like in the next loop, right? So what we can do over here is very simply try to write the iterative code. So I'm not gonna like kind of change this one over here instead, or let's go ahead and like let's write a solve to. Very difficult to change codes and sometimes you might make mistake. Okay, so over here we're gonna paste this one. Okay, and we're gonna go through certain changes. So I'm gonna like remove this thing. This is going to make it much more difficult. Okay, so we take the input, this is going to be solve to, and what we do is like we create we'll write the for loops first. We need to calculate the dp array. So dp of j is equal to so sorry so j is the number of flights, so j is equal to, or I'm going to write I equal to 0. Let's keep j equal to 0. J is less than equal to m. M is now an input as well. Okay, so for I is equal to 0, j is less than mj plus plus, right? And then we're gonna try and calculate for different for integer I equal to 0, the city you are at. Okay, I is less than equal to n I plus plus, right? So we need to calculate the answer for the state I comma j, which is the number of states, the city which you are at, and how many flights have you taken. Okay, note that these two like indexes can actually be altered too. Like you can do the I first and j later, but this is, I have done this for a very specific reason. I'm going to show that next. Okay, so this is the whole code as of now. Let's try to kind of go through this part. So first of all, we write the base cases. So I have already written the code over here, right? So this is the base case over here. So we write same thing over here, no change. Okay, so we write if I is equal to 1 and j is equal to 0, we're gonna have dp of I comma j is equal to, so j is being saved first. Note this very carefully. Okay, this is very carefully. I plus j is going to be equal to 1. It's possible, sorry, it's going to be 0. Okay, or else if I is equal to 0, okay, that's the base case. Sorry, I is equal to 1 and j is not equal to 0. So reaching to the same cell with non-zero number of flights is not possible. So dp of I comma j comma I is gonna return me infinity. Okay, this is what that we're gonna do. Next, we're gonna calculate. What do we calculate? We're gonna calculate the answer for the current state. So we had the code over here. Okay, this code over here. We need to calculate the answer for the current transition. So I'm gonna quickly take this code up and I'm gonna paste it up over here. This answer is nothing but the dp of I comma j, and we're gonna convert the recurrences to dp values as well. That's how we convert like recursive code to iterative code. Okay, and we don't no longer have any notion of like this is going to be j, this is going to be I. So we need to get, we have the same number of buses, like we still have the same number of flights, sorry, but we are going to be at the previous index and we have to come from that index to this one with a bus. That's the cost for over here. And if j is bigger than 0, then we can kind of go through all the different indexes and choose. So this loop is gonna get removed. I'm gonna just quickly do the like not really optimization. Over here we have, let's say, some x equal to 1, x is less than equal to k, x plus plus. I'm just replacing this with x, and this is a feasible code. If j is the number of flights, if j is number greater than 0, then we can do this particular transition as well. Okay. Over here, I think I should write if number is greater than, yeah, that's correct. Okay. If j is greater than 0, if there is some flights left, then we can go through a decreased flight. So this would be saved at dp of j minus 1, I minus x, forget about this recurrence now, plus a of level minus x, which is nothing but I minus x, plus a of I. That's the code. That's the whole code for this one, if you have to calculate it in a iterative way, which looks simple. Like if you had to code this one directly with just iterative code, it's actually simple. In fact, once you're very senior, you can actually use iterative for almost everything. I mean, I preferably use iterative for most of my problems, but yeah, I mean, I'm equally good at recursive as well. So once this is there, you can kind of find out the answer over here using this minimum, and that should give you the direct answer. Like this is the general transitions, that should save the correct answer. Okay, this needs to get replaced over here. Okay, that's the simple idea. But again, we can use the same optimization. Again, we can use the same optimization. Let's try to see. So for this state over here, for this state, we are kind of dealing with, I'm gonna just quickly change the color. For this state, we need to find the minimum of CI values of these. So whatever DP value plus over here, plus, let me go back to the code real quick. DP value of j minus 1, the previous row, and certain I minus x for all different x, plus a of I minus x. So this is nothing but this value plus a of this row. Okay, this plus a of this row, so on. So all those values, the minimum of that is what we want to find. Similarly, for this particular index, you need to find the minimum of these values of the similar type. Okay, so we can again use that same concept of finding the minimum in a window, and we can solve the problem. So what we can do is, for a particular j, we can, so for a particular row, we can create a monotone DQ, which is going to save the minimums of the previous row. So monotone DQ. Okay, and I'm gonna use the same concept over here, like just like over here. If this is over here, for every index, this is the base case. And these all things would be executed in an else. Okay, like if it's not I equal to 1, then only this gets executed. And in that case, we will use the DQ to calculate the answer. So DP of level minus 1, instead of this, I'm just gonna put up j minus 1. Sorry, j minus 1, yeah, with one less flight. At any particular j, when you're dealing with j equal to 0, it should not be handled. Okay, so when j is equal to 0, it is not even using this transition, so it's not used anyways. So I'm gonna just put it over here. Same stuff that I used for that one. Instead, I just added j minus 1 in the over here, because you will do it for the previous row. Whatever the previous row level minus 1 value was, you will insert it, and previous rows level minus k minus 1 value, that will you remove it off the DQ. And now if it is available, you will use it in the DP transition. So over here we did dq.getMin over here. If it is feasible to use them, then we use them to get the minimum over here. So instead of DP of level, we are now gonna have this DP over here. Okay, so that's the whole saved value that we're gonna get over here. That's the whole code, in fact, with an optimization that you, for a particular row, need a minimum of the previous row's window. That's a very complicated solution, actually. If you're watching till this particular point in time, I'm like, seriously, hats off, man. I mean, this is something which is a difficult problem, and if you're trying to learn all these things, I think you would be succeeding quite well in CP. But let's move forward, and because CP doesn't really stop over here. So this is like another way to kind of, let's say, in a 2D grid you can think, or let's say such double parameter states, we can try and optimize things as well. Like for the previous row you can maintain prefix sum, for the previous row you can maintain windows of minimums, and then use that to find out the values. Okay, that's something we can use over here. One more thing that we can try and use an optimization is, like, let's say you wrote this code, but you see that this is actually up to 10 to the power 8, right? And maybe, like, let's say if you submit this code with this DP array with an M into action, I'm just gonna quickly now remove these things. Anyways, I've written this in the video so you can see that while if you want to go back and see this. But this solve is no longer needed as well. We are dealing with 2D version of the things. So we have the solve function over here. If we like create an array like this is quite a large array, right? Sometimes this gives you an MLE because setters want you to give and get an MLE for such a problem, because 10 to the power 8 in time is fine, but 10 to the power 8 in memory is really difficult. Okay, if certainly if you have multiple different arrays. So one thing that you can do in such problems is actually convert this to 2. Okay, because for every j you are only going to depend upon the same j or the previous j minus 1. Okay, so the first optimization was this one, that you maintained monotone DQ of the previous row. The other optimization is that at any particular point in time you need its own context and its previous rows some certain context, right? So these all values will not be used when you're filling in this particular row. Okay, so we can try and optimize this particular thing. The optimization looks very, very simple. I'm going to give you a quick master trick that I sometimes use, is that if you see like you need to optimize it with space sometimes, just take all the DP values, all the places where j is being used as the first index, and take an ampersand with 1. And that's whole code. I mean, like, I just added this ampersand 1 and suddenly the memory memory complexity was around, let's say, m into this was nothing but m into n, right? M into n. Memory was m into n as well. But now suddenly memory is order n only. You have 2 into n. Why is this working? I mean, this is very, very weird, right? I just added certain random and ones, and then it's like magically working at every level. What is this doing, right? Let's try to understand. Okay, so the first things first, you are doing and with 1. Okay, so let's say you are filling in these values. Okay, this is nothing but, let's say, j equal to 0, j equal to 1, j equal to 2, j equal to 3, and so on. For j equal to 0, anding with 1 and like doesn't really make any sense, so it's gonna be just 0 itself. So these, when you're filling in these things in an actual array, in the actual DP array, you're filling in these particular cells. Okay, you're filling in these particular cells. Now when you're filling in this particular cell, okay, for I equal to 1, I equal to 1 means this, I equal to 0 means this. So you are actually filling in this particular array itself, cell value itself. Okay, so I equal to 1, so I minus 1 will mean the previous row, and I will mean like I will mean the same row. Okay, so this is getting copied over here directly. Okay, the interesting thing starts happening from j equal to 2. When you have j equal to 2, j ampersand 1 is going to be equal to 0, and j minus 1 ampersand 1 is going to be equal to 1. So this is like the previous row. So the previous row is actually coming out to 1, and the current row comes out to 0. So you are going to take this values over here, and using this previous row saved over here, you're going to fill in over here. Okay, what happens next? Let's see. For j equal to 3, j and 1 is going to be 1, and j minus 1 and 1 is going to be equal to 0. So for whatever value you had to fill in over here, you are filling at j and 1. So it is going to get filled at 1 using the values at j minus 1 and 1, which is at 0. So whatever you saved in the last row over here is actually present over here, and you are using them to fill in over here as well. So you are actually using these two columns, these two rows only interchangeably, like you're filling in this using this first, and then you're filling in this using this first. The next row kind of gets used with this one. So it's like alternating between the 3 and alternating between the 2, and then like using the previous row information and the current row information as per required, because it is available. This simple ampersand trick makes it very, very simple to code. No more bugging of 0, 1 in the code that you have to write. simple ampersand 1, no change, single line change, and you are done with the whole change for making the space optimization. So this takes down the space from order m into n, which was the initial m in the first dimension and n, to order 2 into n, which is order n. So that is a really interesting space optimization that sometimes is asked. Even in interviews, if you can answer this one, this is like the last level of optimization that sometimes is expected in interviews. So you can actually ace the interview, right? So that's the space optimization that you can use in this particular code. And we now have like very, very optimal code. I don't think I can make it even more optimal than this. But yeah, we have now solved the whole problem in O of m into n complexity, because that's the number of state. Number of transitions is anyways now order 1, because this is amortized order 1. Earlier it was order n into m into k, but now we have made it order 1. So it's n into m. Okay. And that's almost the two optimizations that we were talking about. So the earlier one that we looked was like maintaining a data structure like monotone DQ, or something like, let's say, segment tree at times if required, or let's say simple prefix sums on certain things so that its values can be computed easily and used to optimize the transitions like min, max, sum, and things like that. And space optimization sometimes comes in handy when you have to, like, when you see that the current row only depends upon the current row and the previous row. So you use this alternating technique that you fill in the first row, then second row, then third row in the first row itself because second row is available, then fourth row in the second row, so that because the third row is available in the first one. So that's how you alternate between the two. So that's the two optimizations that we wanted to talk about through this particular video. I wanted to just quickly make some example and give you some idea on this one. Obviously, more and more of these things would be clear when you code these things, right? So that is mostly the main problem solution. What did we learn? So we learned about multiple different optimization ideas, right? We talked about very briefly the state space reduction, which is like if something is already feasible to be created using the other states, drop it off, right? So we talked about state space reduction. We talked about things like the state rotation idea. So definitely check out the AtCoder E problem. That is a very, very interesting problem, and there are multiple solutions already available for that. So you can check that out, okay? Or else we'll do that as a discussion in the live stream. We learned about the transition optimizations, where if you have certain min, max, sum, maybe keeping certain prefix sums of correct values can help you get that value min, max, sum in a order 1 complexity. So that is a transition optimization. We learned about space optimizations, that sometimes you only need the previous row and the current row. So why to save all the rows, right? Just alternate between the first and second row and you will be able to do that. And I showed you a very, very nice way to code the same thing by using ampersand 1, right? So it's like just flipping the parity one by one. That's what it is actually doing. Okay. The next thing that we're gonna like quickly talk about is how we're gonna proceed from over here in the DP workshop, or how you can proceed after this, because this is going to be the last learning sessions. We will have some lives. So the next thing that we will have is day 5 plus day 6 combined live discussion, doubt discussion essentially, because that is something I know I'm pending on. So we'll take that up real soon. Okay. Post that we will also do CSCS problem set. So I think AtCoder's whole problem set is already uploaded on the platform, and you can check that on the YouTube itself. So you can check that out also on the platform, right? And so you can check that out. We're gonna also talk about the problems that we can solve from CSCS, which is almost all of them. And we're gonna having a discussion about that. We're gonna write iterative codes in that so that you can practice more and more of iterative coding in CSCS. And what we can do is we can kind of after that go through the contest that is there for this whole workshop. Okay. So that will be the whole flow from over here. There will be no new learning video as such uploaded. Maybe at times when I think like, okay, maybe this topic can be taken up, I will upload that up. If you're watching till this particular point, I definitely feel that you have enjoyed this session. So feel free to leave down comments to help share this to more people, and definitely help me share this workshop to more and more people, because if I feel that if somebody has watched this video, they truly know the potential of the content that is there in this workshop. So definitely share it with more of your friends, more of juniors who might be interested in learning DP or starting out on DP. Maybe this video is not for the juniors, very, very beginners, but yeah, still you can share it with people, because people do reach out to the same content later on when they find it to be used in a certain problem. So this is something that can be used for that. And we will meet in the next time in a live session or in some other video, or maybe in person if that happens. But that will be all for the DP workshop as a recorded videos. Thanks for joining in this whole workshop. See you in the contest. Hope you win prizes. See you in the standing list, in the winning list, in fact, leaderboard, right? So that's all from my side. Thanks you, and see you all in the next workshop if I post another. See you. Bye-bye.